Okay, so today we'll go through another ANSYS Fluent tutorial. So last week what we did was an internal flow case or pipe flow case. So this time we will simulate an external flow case. And the very simple case we have here is a flow over an airfoil. Okay, what do we have here is a 2D aerofoil cross section, wing cross section or aerofoil. And this particular shape is NACA 0012 aerofoil. And we want to simulate an inviscid flow. So it's not viscous, just an inviscid, simple inviscid laminar flow. And the angle of attack is 6 degrees. So we don't have a uniform, so we have a uniform velocity, but it's not at zero angle of attack, but rather it's at an angle of attack of 6 degrees. So we'll be going through creating geometry for this airfoil, creating the outer domain for our fluid simulation, prescribing the bounding conditions, and then setting up the simulation in Fluent, and then running the simulation and post-processing. So we want to determine what in the end for post-processing of our results. We will look at velocity and pressure fields around the airfoil, pressure coefficient variation over the airfoil, lift and drag coefficients. Okay, as we are going simulating inviscid flow, so theoretically there should be no viscosity effects and hence there should be no drag. But as you know that we are approximating an analytical or solution. So in this simulation, we will get some non-zero drag value, but theoretically the drag should be zero. Obviously, we will get a lift. So in the end, we want to compare our results, how accurate our results are with the experimental data. Okay, so here's a look at our computational domain setup. So here, this white small line is the aerofoil basically. And what we want to do is we want to construct our computational domain or a far field away from aerofoil. So aerofoil has a length of 1 meter, chord of 1 meter, and the inlet velocity. So inlet, this all blue line is the inlet, and in the velocity or the air is coming at an angle of attack of 6 degrees. So the inlet velocity is 1 meter per second, but since we have an angle of attack of 6 degrees, so the x component and y component will be one cos 6 and one sine 6. So they will come out 3.9945, and then y component will come out to be so 1 sine 6 degrees. So that will be 0.1045 meter per second. Then gauge pressure will be zero. Obviously, we will have an absolute pressure of whatever the atmospheric pressure is, 101325 pascals. So similarly, at the outlet, we will have described again gauge pressure is equal to zero, and then aerofoil will be treated as a wall. Okay, so this for the geometry we need the coordinates of this aerofoil, and they will be provided to you or they are given to you in terms of a text file. I'll come to that later. And then there is an experimental result where we are given the experimental lift coefficient value of 0.6630. So that is our kind of benchmark. And we'll be comparing our CFD results with this experimental result. See how much discrepancy we have with regard to this experimental value. Okay, regarding the text file, so in this text file, which says NACA 0012 coordinates, so we're giving X and Y. So we're solving for 2D problem. We have only X and Y coordinates. And then there's a specific template for importing the coordinates into it. This specific template has a certain group column, then there should be a point numbering, then there should be X, Y, and Z coordinates. So we have a specific template which are normally available online. Okay, so it has got 1000 points, and then we have again come back to 0 to close the loop. Close the 2D shape of the airfoil. Okay, so we will import this into our geometry tool in the ANSYS. Okay, so as we did last time, I have recorded this step by step, and then I will explain what to do. So again, you might want to do it. You might just want to see it how it's done, and then later execute by yourself by looking at this tutorial. Okay, so we start workbench again, and we drag this fluent here. We rename it as airfoil underscore inviscid. You can name it anything you want. Okay, then you right click on geometry. Then again, because we are solving for 2D problem, you can go to properties, analysis type, and then you select 2D. Just cross that one as we did last time. Okay, here instead of space claim, we'll be using design modeler. You can use space claim as well. Okay, so you open the design model. It's a geometry creation tool, okay, like space claim. Okay, so first thing what we want to do is, so here we will be building our geometry or computational domain. So first thing we want to do is we want to import our airfoil coordinates. So you go to concept.
Excuse me, sir, can you share that file with us as well?
You want to do it right now?
Yeah, if that's okay.
Let me share. Okay, I hope you have got it.
Yes, sir.
Okay, so you go to the concept in design modeler, and then you click on 3D curve. In 3D curve, you come down here in definition. Definition is that you want to build the 3D curve from design modeler. And then you click on coordinates file and you specify the path or choose the file. Okay, so you go back again. Okay, definition, you choose from here from coordinates file, and then you specify the file there in the second row. Coordinates file. So once that imported, it will be a very small minute structure over here. You might need to click or zoom in, or you might straight away click on this icon over here, and it will give you a zoomed in view. Okay, so next thing you want to do is that you want to create a surface bounded by this airfoil shape. So again, you go to concept, and then you click surface from edges. Concept, surface from edges. Then you click on, so it asks you to select the edges. So you click on anywhere on this airfoil edge, and then you click apply, and then you click generate. So here you will see it will form a surface on this bounded by this outer edges. Okay, so next thing, okay, so next thing you want to do is you want to create the outer boundary or the far field. So for that, we have to do some groundwork and generate a new coordinate system. So you click on this icon over here. Make sure you have XY plane selected. We click on this new plane, plane 4, type, go to the type, from coordinates, at the bottom select from type, at the bottom select from coordinates, and then, so the origin is here initially, but you want to base your origin of this new coordinate system on new plane at the tail of the airfoil. So how you can modify that or transform that? So you select type from coordinates, and then when you select type from coordinates, then you want to shift this. So the chord length is 1 meter. So you need to type 1 there. When you will type 1 and generate, this will be shifted here, a new coordinate system. And then what you want to do is you want to create on this, click on this plane 4 and click on this icon over here, new sketch. this icon over here. Make sure the new plane system is selected before doing this. So click on this icon, new sketch, and in the tabs down below here, you want to select, instead of modeling, you want to switch to sketching. So click on sketch and then click on arc by center. So arc by center, click on this tail point over here. First click on that, then click right up at the vertical and then revolve this around, and then click on the third point below. So you need 3 points. Just click at the center, it will snap to this origin. Click on that, click on the vertical axis. There will be a C letter coming in, just click on that. Make sure you have a C letter there, so C or P, and then you revolve this around and then click it. So it will generate an arc. Okay. Similar, so it's a C-type domain, which is normally used, C-type mesh, which is normally used for this kind of 2D airfoil analysis. It's a very common shape. Okay, next thing you want to do is, then you choose rectangle by 3 points. So click on rectangle by 3 points, then click on this upper point here, upper end of the arc, and then drag all the way down to the lower end of the arc. Okay. So these will be 2 points, and then you want to have a third point. So you just scroll to the right of this line. Okay, so you scroll there, and it will create a draw rectangle. Then you click on this tab, modify, then sketching, and then trim. So you want to get rid of these rectangle side. So you have to click twice, first on this to get rid of the upper half, and then to get rid of the lower half. So that once these are gone, these two halves are gone, then we will have this C-type domain. Okay, so once you have trimmed these two halves, you wanna size your arc and size your this rectangular shape over here. So you go to dimensions again, below modify, and then you click on radius, so dimensions, and then you click on radius, and then you select this arc. And then once you will select this arc, it will give in details over here. You can specify the size of this. So once the size of this radius of this arc is 12.5 meters. So once you have got this thing, so this will be 12.5 meters, and then for specifying the size of this rectangular part on the right hand side, you go, instead of radius, you go to horizontal. So you click on horizontal, and then first you select this vertical line, and then you select this line on the right, and then you can specify the horizontal dimension, which is 12.5 again. So once you are done with the radius dimensions and this horizontal dimension, 12.5 each. Then you need to create a surface over this. So you go switch back to modeling tab. So you can go out of the sketching and you switch back to modeling tab. Then you go to the concept again and select surface from sketch. So you have created this sketch initially in the sketching tab. So you want to create a surface on this sketch based on this sketch. So once you will click surface on this sketch, there will be a tree item here or branch here, which is called surface sketch 1, and it's asking you to select the edges. So you click anywhere on this sketch and then you click apply. So you select this and then you click apply, and then other thing which you want to keep in mind is then once you have selected this, right below that base objects option there is an operation option, and here you want to select add frozen. So add frozen means that you are creating a new entity or object which is different, which is separated from the previous entities you have created, like the airfoil. Okay, so if you click add material, it will just add that object to the previous objects as well. So make sure you have clicked add frozen. So once you click add frozen and then you click generate again over here, so it will create a surface around based on this sketch. So now what we have got is we have got this bigger surface and we have got a surface bounded by the airfoil. And these two surfaces are overlapping at this moment. So what you want to do is you want to subtract or you want to cut out this surface based upon this airfoil. If you zoom in there, you will see two surfaces. So this is one surface bounded by the airfoil, and then we have bigger outer surface. So for that, you go to subtraction, you go to create, and then you select Boolean. So once you will go to create menu and then select Boolean. In the details view, you have to select subtract option. You go to subtract, target bodies. So your outer domain is your target body. Select that, it will turn olive. And then once you have selected that, it will turn blue. And then you go to what will be the tool body. For the tool body, you need to select this smaller surface bounded by the airfoil. Now, because two surfaces are overlapping, ANSYS will show you this option, which surface to choose. It's asking you which surface to choose. So naturally, you want to select as a tool, you want to select this surface bounded by the airfoil. So you just click on the behind on this one so that this one turns red. And once you will select that, this airfoil surface will also turn olive. So make sure that you select the right surface for subtraction. Okay, so once you have turned selected this inner surface, just say apply, and then you generate. So once you will click generate, you will see that the inner, it will have cut out the outer domain, the shape of the airfoil. Okay, so your geometry is, I think, complete. No, not yet. So you go back again. So once you have done the subtraction of the aerofoil surface from the bigger surface, next thing you want to do is, for our subsequent meshing operation, you want to divide this domain into 4 parts or quadrants. So this will be helpful, as you will see later, for our meshing operations. Okay, so to do that, first you need to create on select plane 4 and create a new sketch. So again, click on this. Want to create a new line, a new sketch line. New sketch. Go to the sketching again and select line. Zoom out. And then you start from outer point of this domain, and then you click outside this domain. So you have a bigger line dissecting or crossing this whole domain. From here, and then you click on trim again, go to modify trim, and click on this outer part and this outer part, so that the irrelevant or unnecessary parts are trimmed away. What I've done is I've gone to modify, select trim, and click on here and here, so that only the inner lines bounded by these 2 points is remaining. The outer segments are gone. So what we have done is we have created a new sketch line. And the objective here is to divide this domain into 4 parts. So one part will be this, second, third, and fourth. This will be useful for our subsequent meshing operation. Okay, next thing you want to do is you want to create a line on this sketch. You go there's concept, lines from sketch, then you just select this line which you just draw, and then you select that, and then okay, so once you have done that, so we have one vertical line over here, and then you want to do is, for bisecting this horizontally, you want to create a new sketch line. So you can go to sketching. So again, first select this new sketch, then you go to make sure that you have selected plane 4 before selecting this. So plane 4, select plane 4, and then select plane 4, and then new sketch. It will be a sketch 3 here. Go to sketching, line, and then you create a horizontal line. Again, you want to trim the unnecessary part, so trim this unwanted outer segment and trim this unwanted segment. So you have a horizontal line bounded by the domain. Okay, then you click on concept, lines from sketches. Just select this thing, apply, and generate. So once you have created this line, these 2 lines, now you want to dissect your domain. So for that, you need to project these lines onto this domain. So you go to tools and then you select projection. Choose projection and select edges on face, keep it as default, and then you select first the vertical line, two segments, then click apply, and your target is this domain. Select this domain, it will turn green, apply, then you click generate. If you will see here, the domain has been dissected into two parts. So you want to repeat this again to dissect it horizontally. Again, you repeat the same thing. You select your edges. And then you select this line over here and so this horizontal line and the airfoil shape. Apply, generate, and then you will see that it has been dissected into two parts. Similarly, you want to dissect the right hand side as well to two parts. Again, repeat the same projection operation. Select that edge, other half of the horizontal line. Apply, select the target, apply, and then generate. So the last thing we want to do is in this geometry operation that you want to only export the surfaces, because we will be generating our mesh on the surfaces. So any extra lines like this horizontal lines or vertical lines which we have generated for our dissection operation, we don't want to keep them with us in the meshing stage. So you click on this two parts, two bodies, on this plus icon over here, and then you click on this, right click on this line body, and then you select suppress body. So what it will do is it will just suppress this here at this stage and won't carry it further. So you close that geometry module, then you save it somewhere on your PC. Okay, so here I tried, instead of just refreshing the mesh to read the data, I just clicked on update. So what it did was that instead of following my instructions, it has created a mesh, an unstructured mesh automatically. So you don't want to click on update, you just click on refresh. So once I started the mesher, it did something like this on its own. So that was the result of clicking on update. Actually, what we want is we want a manual structured mesh. So you just clear this. So what I wanted to do was clear this generated data, which it has done automatically. So I don't want that. I just say click clear and generated data. Okay. So you go to mesh again. and double click on mesh once it's done. So it will start the meshing. But this time you'll see you'll just import the geometry over here. So naturally what you want to see is a 2D domain like this. So first thing you want to do is you want to tell the meshing tool that you want to create a structured mesh or a mapped mesh. So you go to mesh. So you go to mesh and or you can select a meshing from this toolbar over here and then you click on faced meshing, or you can go to mesh and right click and you select the faces. Select face meshing and then you select the 4 faces and click apply. So what we'll do is that instead of creating an unstructured mesh, it will tell the meshing tool that we are going for structured mesh. And you want to create the sizing. You right click, insert sizing, or you can just select sizing from here. Okay, so here the sizing will not be uniform. So what we're going to do is that we want to create a non-uniform mesh so that the mesh is more sort of defined or concentrated in the vicinity of the aerofoil, which is our area of interest. So want to see how the pressure profiles or how the velocities or other things. So we are more interested in the area right in the vicinity of this aerofoil. So naturally what we want to do is that when we want to size these edges, we want to do is in a way that we have a more concentrated or refined mesh here in the vicinity, and a sort of as we go move away from the aerofoil in the far field, we have a coarser mesh. So what it instead of so what it does is that if we select more uniform or sorry more refined mesh in all directions in all edges, that will be unnecessary because this is not our area of interest away from the aerofoil. Okay, so that in order to save the computational cost and the computing time, what we're going to do is we want to have a coarser mesh here, and we want to have a more refined mesh here. Okay, so we start the sizing tool. So you select sizing, and it asks you to select the edges first. So we'll do it step by step. So you select first this edge. Make sure this icon is clicked. Edge selection. Let's look at this edge, and this edge. So we have 4 edges selected. Click on apply. So if you look here, so once you select apply, you look here, it says the sizing is uniform. These dark yellow lines says we have initially a uniform sizing. That's not what we want.
Excuse me, sir, ये multiple edges किस तरह select कर रहे हैं?
Which press control when you're selecting the edges.
Okay.
Okay, so once you have done that, it will say 4 edges here, and then you select in the type option, you select the number of divisions. I'll go back. So type is initially selected as element size. You want to change that. You want to select number of divisions, and then you provide 50. Initially, what we want to have is a 50 cells in each line or edge, and then you select behavior as hard behavior as hard. Okay, so for creating non-uniform mesh, there is a function over here at the bottom which says bias type. So you click on bias type, go back, click on bias type and select the first option. So there will be dotted lines. There will be 4 rows of dotted lines. You want to select the first row of the dotted line. So what does it mean is that towards the left, we have more refined, more smaller concentration of cells. And as we move away, we have a coarser mesh. So in the dotted lines, you want to rows, you want to select the first bias type. Okay, and when you select first bias type, it asks you to determine or prescribe a bias factor as well. So you select 150 there. Okay, once you will click that, you will see that instead of now uniform divisions, we have a non-uniform divisions. We will show you a pattern. So you see near the airfoil, we have more uniform divisions here, here, and here towards the aerofoil. And as we move away from the aerofoil, we have more coarser divisions. Okay, I'll take a break here. And then I join you after 5 minutes. Okay, we are back online. Okay, so once you have done this biasing, distribution will look like this. Similarly, you want to create biasing on other sides as well. Click on edge sizing again. Select side, pressing control. Yes. So these will be four sides which turn green. Select apply. And again, you want to select the number of division. Right here. Change the behavior to hard and bias type. Now you select the second rule says like this thing says that more course towards this side and more. You select that, you see distribution pattern like this. So more biased towards the airfoil and the airfoil. So and then you select depending on, so you select new sizing again, and now you select the curved surfaces. There are one and two curved surfaces here and two curved surfaces which form the C. One and this one. These four will be third sizing option. Select temporarily, and here you select the soft, turn that to hard, and then here you keep no biasing. Okay, so you keep a distribution. You can change it and try with it. Make the mesh more biased. I've kept this as. So once you've done that, then you click on mesh and then you click generate. So sometimes it gives this error. I tried a couple of times. Sometimes it gives, sometimes it doesn't. Right here, it might not. Leave that, ignore that moment. So once you click generate, it has created a structured mesh around this arrow. And then you see this is a non-uniform mesh. We have smaller cells near the airfoil in order to capture flow physics more correctly, and we have a coarser distribution away from the airfoil. So this is something which you want to keep in mind, that always refine those areas which are of interest, and always coarsen those areas in order to have a computational efficiency. So ignore this here. It's showing the biasing. This step Okay, so some mesh at this stage is complete. Next thing we want to do is, as we did last time, that we want to name our boundaries. So you name first the outlet, select the outer edges, create name selection, right click on that, create name selection, and then type outlet. Okay, at the inlet, make sure you have this curve selected, this C curve, and also these two horizontal lines. So first select this, also select these two here also described as, and right click here, create name selection as inlet. Okay, so and then you zoom in there and you want to select this airfoil and name it as airfoil. There will be three boundaries, boundary names: inlet, outlet, and airfoil. You can check the sides again with that. Make sure you have selected the right.
सर ये क्वेश्चन है
We will proceed. Okay, then you double click on setup. Here you choose region option. Okay, last time what we did was that carried on these and also have a parallel computation which will involve more process. So here you can specify the number of processes. Of course, if you have large machines, then if you have a so much powerful source, just leave that as one. If you have more available, then you can use the number. Obviously, for bigger machines or clusters, we much higher number of clusters here. We have a GPU cluster. So describe that here. Okay, so here I've selected two only. We'll have a more faster computing instead of one. Click double precision. You want to leave that as one or two, whatever you want. Okay, so you let's start. So it will read in the mesh and the boundaries. So blue, red here you will see with different colors because it has identified as different boundaries. Display the mesh by one or all the parts have been put. You can also analyze size 15,000 cells I have here. Make sure that this airfoil shape has been rightly imported. Okay, here you want to choose solver as density based. These are more useful for, so generally pressure based are used for incompressible and density based are traditionally used for compressible, but here you might want to try density based. You can of course try pressure based as well. It won't make much difference at this stage because our flow regime is essentially incompressible or sort of flow regime. Its mag number is lower than I think 0.3. So you can, if you want, you can try out pressure based as well. I've selected this density based. Go step-by-step process. First, you want to tell Fluent that you are going to solve an in-visit flow problem. Double click on viscous. Select in-visit, the first option. Next thing, I want to prescribe the materials fluid air. Double click on air, and here you want to using just a density. Make sure constant is checked, and you select 3 parameter. Change that value to 1. Okay, so that is done. Next thing, as fluid, nothing to do in cell zone. Boundary conditions, double click on boundary conditions. We want to set, make sure you have the first thing or inlet. It will say the type. By default it has selected velocity inlet. That is fine. Click on edit, and here you want to change the velocity specification method. At velocity inlet, you want to change that to, you want to select components as an option because we have 2 velocity components available. It's horizontal 9945, and the other one is y velocity component is 0.1045. So instead of giving a whole magnitude, we are just selecting components, and then once you have selected components, you want to prescribe the values here. Just type the values. So this is 1 equivalent to 1 cos 6 degrees, and this one is 1 sine 6 degrees because we have an angular attack of 6 degrees. That's okay. For the outlet, make sure that pressure outlet is selected as the type. And make sure that gauge pressure is 0 in all these. Okay, at the airfoil, show that all foil type A. So that is done. And next, you want to set some reference values. Just select compute from inlet. You will see that compute from inlet. It will automatically pick the values which you prescribed as in the inlet boundary conditions. For example, there you prescribed density as 1 kg. So these reference values are used later for calculating various coefficients like lift coefficients, drag coefficients, pressure coefficient, etc. Okay, so you have select prescribe reference values down to the solution module. Then double click on methods. Here, you click over here. Formulation is implicit or explicit, and flux type is a numerical scheme. It is called rho flux difference scheme, and then you have a gradient, and then you have a flow option. So make sure, I will come to that later once we cover the theory, what are explicit and implicit schemes and what are other specific options we have in these implicit and explicit schemes. So at this stage, you don't want to do anything, just keep it or leave it undisturbed, and then make sure you, in the flow tab, you have second order upwind. Second order upwind, it is selected already, leave that as it is. Okay, next, to monitors, then you double click on residuals. So in the residual monitors, as we did last time, you want to change that to your tolerance level further down, change that to 1 into 10 raised to the power minus 6 for all residuals, continuity and momentum. So once you have done that, you click OK. And next thing you want to do is you want to initialize. Yes, initialize. And then you click on standard initialization, viewed from inlet. So initialization means just start with the inlet conditions. Or if you know, for example, if you are simulating your solution for a second time for more, for example, if you change something, then you want to prescribe more accurate values of velocity here. But since we are just running it for the first time, you want to just tell the fluent that just pick up the inlet values at the initial solution. Okay, so then you can double click on run calculation, check case. It asks you to check your mesh. There was something, maybe some quality of the mesh is not that great. Fine tune that, but leave it as it is. And in the number of iterations, you just prescribe the number of iterations to 3000. And then you click on calculate. So once you do that, you have to wait for some time and look at the convergence process. Just fast forwarding it. So one thing you will observe is that the convergence pattern or trend here is not that much smooth as compared to last time. So there might be various reasons for this. The initial solution is not that great, or the mesh quality is not that great, or specific scheme is not behaving well. So there might be various options, and you will see this wiggles many times. So the ultimate thing to observe is that there are no overshoots, there are much larger variations, and the convergence process doesn't have a repetitive pattern. So if you see here, it is wiggling, but it is going down. So that is okay, as long as the slope is like that. Although it's wiggling, but the trend is on the lower side. So that is okay. Okay, so after a certain time, certain number of iterations, more than 2500, it has the process is complete. Okay, so our solution is there. Next thing we want to do is we want to observe the results. So you click on, so here I'm not going to CFD post. I'm just quickly analyzing my results here. As I told you earlier last week that you can also generate your results here within the. So it's up to you whether you want to CFD post or generate your results here. Okay, so I click on graphics in the results. I click on graphics, and then I click on vectors and see the flow vectors. So I double click on vectors. So vectors of what? Vectors of velocity and vectors colored by velocity, and the parameter is velocity magnitude. Okay, so display it, zoom in. Okay, so you want to change the length of the vectors. So I have divided by 10, 1 by 10 will be 0.1. Then you see a beautiful vector plot. Is the flow vectors. Red means high velocity and blue means the lower velocity. So here's a gradient legend. Then you want to see the contour. So you double click on contours, contours of velocity and velocity magnitude, and then explain. You can see the. So here on this upper surface, we have a flow acceleration. So it's like velocity of 1.55 meter per second. The lower side, we have a sort of lower velocity, and then as here we have a lower velocity region as well. In the far field, we'll see more green. That means that the far field, the velocity is more sort of constant as expected. Okay, you can also analyze contours of pressure and static pressure. Leave that here, a region of lower pressure on the upper surface. High pressure on the surface. So it's not a symmetric profile on both ends because we have a angle of attack of 6 degrees. So contours of velocity, you can also draw contours of stream function. You have to twiddle that a bit, change that range. Maybe you just try 13 to 14. You go to color map options here and tweak that further. Just skipping that. It's not very good. Okay, next thing you want to do is you want to create a plot for the pressure coefficient over the airfoil. So you click on plots and then XY plot. Double click on XY plot, and then you want to select the pressure as y-axis function. Change that to pressure coefficient. X-axis remains the direction vector. And we want to see the pressure coefficient over airfoil. So you select airfoil and say and plot. Okay, so this plot is giving you the pressure coefficient values, the upper and lower surface. You might want to compare it with some experimental data if that is available. So you can, and you can also write this point values as dedicated file. Okay, so you click write to file and then write, and then you can save this data, for example, Excel, or compare it with some other result. Okay, so last thing we want to do is to monitor or calculate or determine the values of drag coefficient and lift coefficient. So you go down, and instead of plots, you go down to reports at the bottom. Then you click on forces. Once you double click on forces, it will automatically select airfoil because on this surface wall force is there. All boundary conditions airfoil. Okay, so for the lift coefficient, so if you look here, the lift and drag will look like this. Okay, so you want to prescribe the x and y components. The x component will be minus 1 point something, 1.0, 0.1045, and the other component will be 9945. I'm just prescribing that here. So 0.9945, and then look here. If so, once you select print, here in the console here, you will see it will show a value 0.6223138. And if you compare that to our experimental value, that was lift coefficient was 0.6630. So it's pretty close to that. But if you want to have a more closer accurate value, one of the approaches is that you want to refine your mesh. Okay. Similarly, you can also observe the, so we say 0.9945 and 0.1045 as factors. This will give you the CD value. Now, as I said, because we are simulating inviscid flow, theoretically CD should be 0 because we have no viscosity effect. But here it's giving a non-zero value because we are approximating, because the simulations are always approximations. So this is something we want to ignore. We don't want to, theoretically the value is 0. Okay, so that basically completes with the this tutorial. Now, next thing you want to do is, as we did last time, that you go back to the mesh and you double the first two edge sizing too. So first two edge sizing were 50 each. So you want to double that and then rerun the calculation and see if the value of the lift coefficient improves or not. So that's something which you want to do or try at home. Okay, any questions? Questions? Okay, so as long as we have this distance learning DL mode on, I will try to cover as much tutorials as possible, and maybe towards the end of the semester we will try to cover the rest of the theory. And if possible, if something is important, is necessary for tutorials, I will cover that theoretical part in between as well. I'll keep giving you assignments so that submit those actors references fluent also. Any questions?
अस्सलाम वालेकुम सर। सर आपसे
जी।
पूछना था कि लेक्चर की रिकॉर्डिंग्स कहाँ पर अवेलेबल है?
लेक्चर्स की इसी जो मेन टीम्स की चैट है उसमें आई थिंक आई हैव बीन अपलोडिंग द रिकॉर्डिंग्स। ये फाइल्स में नहीं होंगी, ये जो मेन डैशबोर्ड है टीम्स का उस पर स्क्रॉल अप विल फाइंड द रिकॉर्डिंग्स।
Oh yes sir, I didn't observe. Thank you.
सर मेरा एक क्वेश्चन है।
जी बताएं।
सर मैंने ये पूछना था, जो हमने डोमेन की पार्टीशनिंग की है उसका हमें फायदा क्या है?
ये जो हमने बाद में मैशिंग में जो हमने एज साइजिंग की थी, ठीक है, उसके लिए ये हेल्पफुल है, क्योंकि अदरवाइज अगर हम वो पार्टीशनिंग ना करते तो जो एजेस थे जिनकी हमने प्रिसाइज डिस्ट्रीब्यूशन की थी एजेस की बाद में और बाइसिंग की थी, वो हम ना कर सकते। अदरवाइज व्हाट वी हैव डन वाज कि हमें एक एज हमें मिलना था एरोफॉयल का और एक हमें वो होल सी डोमेन मिलनी थी, ठीक है। तो जो स्ट्रक्चर्ड मैश है उसके लिए दैट इज नॉट हेल्पफुल। इफ यू विल जस्ट if you will just distribute the points on the aerofoil and on the outer C mesh, you will see that the mesh quality will be very bad, and even in some cases feasible जो workable mesh है वो भी नहीं generate होता। So partitioning is a sort of what we have done is we have created a multi-block structured mesh. तो जैसे जैसे complexity increase होती जाती है, we need to create more blocks and more partitions for our structured meshing. So this is one of the sort of disadvantages for structured meshing, that it doesn't efficiently handles more complex geometry. तो आसान सी geometry थी, so for that we need unstructured meshing. We'll come to that later as well, but structured meshing का advantage ये है कि this is more accurate than unstructured mesh. इसमें discretization errors कम है as compared to unstructured meshing. So दोनों के plus and minuses हैं. So for simple cases you want to prefer structured meshes, and for more complex 3D geometries prefer unstructured meshes. Any other questions? Okay, that's it for today then. Thank you.